Good morning, students. It is Monday morning, and I'm getting ready to give you some notes about electric fields. This assignment will be due next week. I think the date is May 4th, and I'm giving you a different view of my dining room. This is my cat, Frankie, who is looking out the window, hoping to see a bird. He's a good boy. There's a few other cats around here. I'm not a dog person, I'm a cat person. He loves it when I scratch him. All right, so I'm gonna get rid of my face and open up this electric fields template. You have access to this if you'd like to use it. Otherwise, you can just put these notes in your notebook. And if you don't feel like you need the notes, I'm not going to be able to check them. But I think it is helpful to have written something down. Educational literature says that if you write it, you incorporate it in your brain. And so here we go. Electric fields. Get rid of my face. All right. So what I'm going to do is try to relate electric fields to gravitational fields. I know that you learned about gravitational fields, and I know that you have some experience with gravitational fields. And so let's remember what we know about gravitational fields. What is a gravitational field? Basically, it's an invisible region in space which affects masses. And that's because the force of gravity is an attractive force between masses, right? And so we drew the picture back in October of the Earth, and we drew this invisible field as a set of lines pointing down all around the Earth. Kind of looks like that, right? And we even gave it a name, G. G. So G is the gravitational field around the Earth, and it's invisible. We don't know it's there unless we lift something up and we notice that it drops to the Earth. It's like magically attracted to the Earth. And you've been noticing that since you were born, since you were little. You've grown up in this gravitational field, so it certainly doesn't seem strange to you, right? And so we also know that we have this force formula, Newton's law of gravity. And what does that equal to? Big G times the mass of the Earth times the mass of whatever it is that you're lifting up. So let's call it the mass of some other object divided by the distance squared. This gives us the force between the Earth and the object. Earth and the object. All right. And so if I pick this apart, this much of this formula is G. That is G. And so what I really have there is that the force of gravity is the mass of some object, whatever the object is, times G. And I can write G using this formula. All right. And so G is incorporated in the force of gravity formula. And we oftentimes write this as the weight of an object, the pull of gravity acting on a mass, the mass of the object. Okay, that's an object's weight. Okay, so just a little review of gravity. Now let's go on to electric fields, which you know have a formula that's very similar to the force of gravity formula. It's called Coulomb's law. And so I'm going to draw a similar picture, and I'm going to talk about electric fields in a similar way. And so what is an electric field? That scratching that you hear is my cat scratching on his scratching post. Different cat this time. So for an electric field, it's an invisible Arthur, that's enough. Invisible region in space, surrounding not a mass, but a charge. Invisible region in space surrounding a charged object. Okay, so it's important to know that gravitational fields affect masses and electric fields affect charges. Invisible region in space surrounding a charged object. In fact, it's the charge, oops, I shouldn't say that. It is the force per unit of charge. So it's the electrostatic force that acts on a single unit of charge. Now, I could have written gravitational field the same way. Looking at this formula here, I could write G as the gravitational force per unit of mass. All right, force per unit of mass. That's kind of a nice way to think about a field. The force per unit of mass, or in the case of the electrostatic force, it's the force per unit of charge. And instead of little g, we give this electric field the symbol E. Okay, now if I look at Coulomb's law, remember Coulomb's law looks like this. The electrostatic force is equal to K times the charge of one object times the charge of another object divided by d squared. I could write this very similarly as this much of it is E. That's the electric field. And so I could write that the electrostatic force, this electrostatic force here, is really the electric field multiplied by the amount of charge that's present. So it's very similar to the force of gravity. The electric field is the force per unit of charge. Or I could say that the electrostatic force is the electric field times the amount of charge. All right. So now if I draw some pictures. With gravitational field, we were drawing the Earth as this huge mass. Now we're drawing a tiny little proton, or a tiny little amount of charge. And what does that charge do to another positively charged object that might come nearby? It pushes it away. So that positive charge there pushes away another positive test charge. So here's my little positive test charge. It's going to feel a force away. All right, so the electric field around a positive charge points away. That tells me that it's repulsive. All right, what about around a negative charge? Well, the electric field around a negative charge, what does that do to a little positive charge if I were to stick a positive charge out here, a little test charge? Well, it draws it in. It's pulled this way. And so around a negative charge, the electric field points like this. It pulls positive charges in. And this reminds me that I need to go back and alter my description of electric field because I left out a pretty important part. So I'm going to go back and do that in a second. So around a negative charge, the field points inward. And that tells me it is attractive. Okay, so let me go back and alter my description of electric field. Invisible region in space surrounding a charged object. It shows the direction of force on a positive test charge. Shows the direction of force on a positive test charge. And here in Coulomb's law, this is going to be a little positive charge. The test charge is always positive. All right. And so here, that's why in pink or whatever this color is, raspberry, I've drawn my little positive test charge. That is a test charge. Okay, so whatever happens to that charge, that tells me the direction of the electrostatic field, the electric field. All right. Section 33, I believe it's 33.3, talks about electric shielding. That's what happens if you're sitting inside your car in a lightning storm or in any conductor, but cars tend to be made of metal. So let's just draw a big old conductor here. It doesn't even have to have an important shape, any old shape at all. It's a conductor. And what does that mean to you? It's made probably of metal, and so it's got lots of free electrons, and the electrons carry any excess charge. Well, what happens if I put an excess charge on this conductor? Since the electrons are free to roam, all of those excess charges will immediately go to the very surface. So if I dump a lot of excess negative charge on this conducting blob, all of those excess electrons, they're not going to reside in the middle. They're not going to be in here because they want to get away from each other, as far away as they could possibly be. And so what do? They reside at the very outside surface, at the very edge. And that means something important. That means that the electric field is exactly equal to 0 inside a conductor. Even if there's a negative charge on the outside, and that might mean that there's an electric field outside the conductor, right? Negative means it's pointing in, pointing in, pointing in, and here's my electric field, E. Inside the conductor, there's no electric field at all. There is no electric field at all. And that is true of any conductor. And so that's the real reason you are safe if you're inside your car in a lightning storm. It has a little bit to do with the tires being rubber, but mostly it has to do with the fact that you're inside a conductor. And if you were hit by lightning, all of that excess charge that the lightning bolt carries would be immediately found on the surface of the conductor, not on the inside. So you are safe inside your car during a thunderstorm. All right. Excuse me. On to potential energy. So let's go back to fields. Here's the surface of the earth. Here's a random person standing on the surface of the earth. And you remember what we said about potential energy. There's this gravitational field around the earth, G, it points down. If I take some object, any object at all, and I lift it up to a different height, it's going to have some potential energy at that height. Potential energy. And we describe potential energy as stored energy. In fact, it's stored energy due to, what does that say? Due to position. Stored energy due to position. Why? Because that mass would like to be on the ground. And if we lift it up, it's going to move to the ground as soon as we let it go. So that's stored energy, potential energy, we described as mass times gravity times height, or really force of gravity times the height or the distance. So remember that. All right, so now what about electrical potential energy? Well, if I have myself, instead of the earth, a positive charge, and I stick another charge near it. Let's consider a negative charge now. Let's say I have a little negative charge. Where does that negative charge want to be? Well, it wants to be stuck to the positive charge. They are attracted to each other. Just like this mass wants to be stuck to the surface of the earth, this negative charge wants to be stuck to the proton. So if I lift it up what's it going to have? It's going to have some potential energy, right? And so potential energy due to the electric field is really stored energy due to position. Same idea. Wants to be stuck to the positive charge. If I remove it, it's going to have some stored energy. What does that have to do with anything? Well, when we use a battery has a positive end and a negative end. And those positive and negative charges would like to be together, but they're not. They're separated. They are forced to be separated. And that means there is potential energy stored inside that battery. All right. Now, since charge is very, very small and sort of hard to count up individually, individual charges are hard to count, we use a term that's called electric potential. And what that really means is electric potential energy per unit of charge. Electric potential energy per charge. Okay, and so electric potential is known as voltage. And the unit is a joule per coulomb. And that makes sense because a joule is energy and a coulomb is charge. All right, potential energy per charge is known as electric potential. And that is where we will stop this week. I hope that you have a great week. I hope that you have success with the worksheet. Next Monday morning, please take a look at your answers and make sure they're correct. And we will be going on from here to talk about what we can do with batteries, put them in circuits, and run things. All right. Have a good day. Bye.